My name is Jörg Waschul. With this slideshow, named Cold Storage Devices for Smart Grid Integration, I would like to give you a short summary of the results of one of our recent research projects. Why do we talk about cooling technologies in the context of renewable energies and smart grid? To answer this question, I would like to give you some figures. 14.2% of the electricity consumption was caused by cooling and refrigeration technology in 2009 in Germany. If we have a look on the distribution over different sectors, we find that the main contribution is given by domestic refrigeration with a share of about 1/3. Other important electricity consumers are industry, air conditioning, food production, and supermarket refrigeration. So it is worth to think about the role of these technologies in the future energy supply system. At first, we should have a look on the normal operation mode of a compression cooling refrigeration system. This is the on-off mode. As an example, you see temperature measurements of an empty household refrigerator. When the temperature in the cooling cabinet is too high, the compressor starts, and when it is cold enough, it stops. The short red lines mark cooling periods, that means periods of energy consumption. These periods depend only from the temperature behavior of the cabinet. There is no feasibility to adapt the energy consumption to variable tariffs or demand and supply variations. Therefore, the question in one of our recent research projects was what technical precautions would be required to make the energy consumption of cooling systems more flexible in time. We started with a normal refrigeration system we didn't want to change very much. It consists of compressor, condenser, expansion valve, and evaporator. When we want to design a flexible cooling system, we need at first a cold storage. As a second component, we need a heat transfer control element. Explanations on this I give a little bit later. The third component we need is a state of charge sensor for the storage, and last but not least, a communication interface. The red marked components were subjects of our project. We carried out theoretical and experimental investigation on these elements, and we converted a commercial refrigerator for demonstration purposes. To design the cold storage, we investigated different evaporator geometries and cold storage materials, in our case eutectic salt solutions. Our choice for the demonstration model was the combination shown on the right hand side. A thin tube evaporator with potassium bicarbonate with a melting temperature of around -6 degrees C. The second focus of our work was the heat transfer control element. This picture is a sketch of a thermally isolated room with an integrated cold storage. Most cooling applications require constant cold room temperatures. Ice storages deliver fairly constant temperatures, at least at the solid-liquid phase interface. But under real conditions, we have a number of disturbing influences. For example, door openings, different ambient temperatures, or exchange of goods. To level out these influences, we need a heat transfer control element. As an additional requirement, we set to ourselves that the heat transfer control element should run self-operated, that means without any electricity. As a solution of the task, we designed a looped and valve-controlled thermosiphon, which is drawn in orange in the sketch. A working fluid condenses in the cold storage. The self-operated temperature regulator releases working fluid in dependence on the cold room temperature. Over the planar heat exchanger, the working fluid absorbs heat and evaporates. During that process, the cold room is cooled. The gaseous working fluid returns to the cold storage and the process starts again. This whole temperature control process is totally self-acting and does not need any electricity. As a third required element, I mentioned a state of charge sensor. There are a number of phase change effects which can be used to measure the state of charge of PCM storage. We decided to utilize the volume change during melting and solidification to generate state of charge signals. As a sensor element, we integrated a conductive silicone membrane. The electrical resistance of the membrane varies with its strain. On the slide, you see details of the demonstration model. The black box is the cold storage and the attached dome is our state of charge sensor. At the left-hand side, you see the membrane at discharged storage, and on the right-hand side, the charged cold storage. The next slide shows the electronic control unit of the demonstration model. It is microprocessor based and required for the determination of the state of charge of the cold storage, detection of energy supply information, and the deduction of switching decisions for the cooling unit. It is equipped with a real-time clock, several buttons, and Wi-Fi connectivity. On that picture, you see the demonstration model with control unit, cold storage, temperature regulator, temperature sensor, and planar heat exchanger. Our model consists of a standard domestic refrigerator without freezing compartment and a capacity of 290 liters. The cold storage has a volume of 13.5 liters, which provides a thermal storage capacity of about 0.9 kilowatt hours. The thermosiphon heat exchanger area adds up to 0.4 square meters. As a working fluid, we used R134A. This slide gives an impression of the operating performance of the cold storage device. X-axis is the time over 2 days. The red curve is the cold storage temperature and the green curve the cold room temperature. Both curves belong to the left y-axis. The blue curve is the resistance of the state of charge sensor. At the beginning of the experiment, you see the cool down process, initially with closed temperature regulator valve. At point 1, it was opened to a certain set point. The cold room temperature fell rapidly, and after a short overshooting, it stabilizes at around 8 degrees Celsius. In point 3, the refrigeration unit was switched off due to a full storage signal, and in point 4, the set point of the cold room temperature was decreased to 5 degrees C. Due to exhausting storage capacity, the cold room temperature exceeded 6 degrees Celsius in point 5. That means, in this case, we have more than 30 hours between switch off of the cooling unit and excess of a certain temperature. The resistance curve of the state of charge sensor increases steeply during the charging phase and shows a smooth and nearly time proportional characteristic during discharge. The operation performance of the demonstration model can be summarized as follows. The operation is independent from the grid for more than 24 hours at 5 degrees C cold room temperature and 22 degrees C ambient temperature. The lowest achievable cold room temperature is 0 degrees C. The maximum adjustable cold room temperature at an ambient temperature of 16 degrees C, this is also an important parameter, is plus 7.5 degrees C. The temperature constancy inside cold room is about plus minus 1 Kelvin. The accuracy of the state of charge determination we estimated to about plus minus 10%. The average power consumption during storage charging is 135 watt, and the average charging time within 24 hours at 22 degrees C ambient temperature without load is 3 hours and 17 minutes. But what is the result of all these technical efforts? The cold room temperature can be maintained independently from continuous energy supply. The system is now free for an optimization of energy consumption times. Some examples how this can be done will be given in the next slides. With the cold storage system, one is now able to take the state of charge as reference value for the operation of the cooling unit. Again, the red lines mark the operation of the cooling unit. And these red lines indicate a simple exchange of the reference value, that means state of charge instead of temperature, does not give any advantages in terms of flexibility of energy consumption. To control the operation in terms of energy consumption, it is necessary to have more than these two levels, which is shown in the next slide. As an example, we can introduce two pairs of switching levels. One pair near full charge of the cold storage and one pair close to the discharged state of the storage. If there are now preferred energy consumption times like the night in case of night tariffs or the day in case of utilization of PV energy, one simply has to swap the activity of the switching level pairs. The result of this operation mode will be the desired energy consumption pattern. The predominant fraction of the energy consumption takes now place in the preferred times. In our demonstration model, we implemented this operation mode using the real-time clock of the microcontroller. If the preferred energy consumption times occur randomly, 3 switching levels might be enough. This could be the case in energy systems with fluctuating sources, for example, to increase self-consumption in PV systems. 2 switching points are required to keep the storage on a low charging level. Then the storage is able to absorb cold when the refrigeration unit starts running on an external trigger signal. The third level is only necessary to switch off the cooling unit in case of full storage. We integrated this operation mode into our demonstration model using the Wi-Fi connectivity. And last but not least, when the 2 main switching levels are in the middle of the storage capacity, the refrigeration system is able to provide balancing power. This slide shows the example of positive balancing power when the cooling unit is switched off by an external signal from the utility. Negative balancing power one could generate by switching on one or more cooling units. To avoid synchronizing effects, the third corresponding switching level may be different from system to system. Let me summarize. Cold storage technologies, in combination with appropriate peripheral components, that means state of charge sensors, control and communication elements, provide the capability to act as a compensating part in energy supply systems with fluctuating sources. Other fields of application are the optimization of self-consumption of electricity from photovoltaic system, the operation with variable electricity tariffs, and refrigeration systems for regions with unstable energy supply. A high-resolution state-of-charge sensor and an independent cold room temperature control are essential for optimum exploitation of the benefits of a cold storage. And as an important point, I want to emphasize that the demonstration model presented here is just one small-scale example for a great variety of conceivable cold storage application with interesting feedback to the electrical energy supply. With our last slide, we want to thank the German Federal Ministry of Economics and Technology for funding of this project and you for watching this small presentation. Thank you.